Hi,
Hello,
Paul.
everyone. Hello, everyone, and thanks for having here. I apologize for not being there in person. Today, I wanted to talk about some of the intriguing new results that we've learned about from Parker and Solar Orbiter. In order to do that, though, I need to give you a few comments on what we did know before Parker and Orbiter, just to remind you, and then describe some of these new results and how the picture of how the solar wind emerges and the heliosphere is created from the solar corona is rapidly changing thanks to some of these observations. So this is a reminder of what the corona looks like in two different periods of solar activity. On the left, you see the total eclipse of 2017. We were still fairly close to solar minimum. And so you can see the very, very strong asymmetry of the corona. And you can basically see that the polar coronal holes have these plume-like structures. These are called coronal plumes from the north and south poles. There is an equatorial belt around which you can see these what are called helmet streamers with various rays and stock. There's a beautiful prominence sitting here. This up on the top, right, is something that looks like a helmet streamer, but is not really. It's what's called a pseudo-streamer, because we know from mapping the magnetic field that the magnetic field on this side and on this side of that structure has the same side. While when we cross over here, we change the polarity of the magnetic field. Now, at solar maximum, of course, anything goes in the sense that we lose the plume appearing in the poles, but we kind of see this streamer, pseudo-streamer structure everywhere in the corona. And this is just a photo taken by a photographer on the 20th of April of this year. This picture doesn't show as many prominences, even though there were many more than in 2017. It's a question of contrast and things like that. So what we do know about how the solar wind changes over the solar cycle mostly comes from the Ulysses spacecraft mission that ended in the early 90s and that went over the solar poles. Actual fact, it ended in the final. Its first orbit was in the early 90s. It ended in the late 2000s. But what you see is that at solar minimum, you have this beautiful dichotomy of the way the heliosphere and the solar wind responds to the structure in the corona. You have a fast solar wind. This is a polar plot of solar wind speed. You have a fast solar wind emerging from the high latitudes. And then you have a streamer belt where there is an oscillation between slower and faster speeds, and this contrary goes on at the other cycle. At solar maximum, again, we have a mix of high and low speeds all over the place. It's, in other words, the confinement that the corona provides is changing dramatically. It doesn't really, there's no obvious dependence on latitude or on heliolatitude. Let me just say that the solar wind that you see here has an average speed of somewhere around 750 kilometers per second, but you can see that even in the polar wind, there is a turbulence. I mean, there is a structure, and that structure has an amplitude min to max of about 80 kilometers per second, plus or minus 40 kilometers per second. Intriguingly, in this solar wind up here, a small discovery was made because sometimes the magnetic field actually reverse polarity. Here, red and blue indicate the outward and inward interplanetary magnetic field. It shows that 11 years later, the polarity has reversed. So indeed, there is a solar dynamo if somebody didn't believe it. And so on. But what this observation showed was that there was some blue in this red up here. In other words, there were regions close to the poles, especially clearly visible, where the radial magnetic field inverted itself. However, this inversion was not really a disconnection. It was not a polarity inversion that extended down to the corona, but it was really a fold in the magnetic field. And this was called a switchback. This turbulent structure here that has a periodicity of about a day was called a microstream. So what do we know about this fast wind in the coronal holes? What we do know is that the coronal hole solar wind is extremely hot in minor ions. This is the temperature as distance, thanks to the SOHO mission UECS measurements that show that the temperature goes up to several million degrees. This is the acceleration profile of the wind from radio data, and it shows that the solar wind accelerates to fairly high speeds pretty rapidly. And finally, there's this anti-correlation between what's called the freezing in temperature and the solar wind speed. So in other words, the coronal hole, and as you can see, it's confirmed here, the electron temperature in a coronal hole is fairly low, while the electron temperature in the slow wind is much higher. So this is basically the dichotomy at solar minimum. And again, I'm not going to really be discussing solar maximum in detail, because the situation is much more complex as you have confined and non-confined fields together. Now, of course, this raised really intriguing problems. The Parker solar wind, an isothermal corona, will never get you to 1 AU at 730 kilometers per second, or 750 or 800. A million-degree corona, if you look at the electron temperature here, it's less than 1,000,000 degrees, essentially, in the coronal hole, will only get you to about 250, 300 kilometers per second. So this raises the question of the coronal acceleration profile. It also raises the question of the thermodynamics, because it appears that the Lyman alpha, neutral hydrogen measured via Doppler dimming and line widths, goes up higher than the electron temperature. What can help? What can help is the fact that you measure a spectrum of turbulent fluctuations in the solar wind. This is, again, a mix of data now at different distances from the sun. The larger distances from the sun that you see here is Ulysses. Closer distances to the sun, 0.3 astronomical units, is the Helios data as a spacecraft, a German spacecraft from the 70s. And what this showed is that there is a turbulence with an energy containing range which looked like an f⁻⁻⁻⁻⁻ spectrum. I may remind you, an f⁻⁻⁻⁻ spectrum means that the energy in the fluctuations is equipartitioned over all the different scales. So that's called the energy containing range. That gets eaten up as you move away, and you get something like an inertial range, which remarkably is close to what you would expect on hydrodynamic turbulence, Kolmogorov. And that was the fast wind. The slow wind typically showed lower general energy, even though it would not appear so in this picture. It's an issue of normalizations. And a well-developed spectrum of turbulence all over the place. There's an additional major difference in these two regimes. The other that I'm going to have to mention is that the fast wind is permeated by large amplitude Alfvénic fluctuations. These are essentially the Alfvén waves that were invented or discovered by Hans Alfvén in the mid-40s, and were discovered in the solar wind very quickly, the first satellites that went up. And the fast wind displays these waves. This is not the sheer Alfvén wave. This is a macroscopic large animal called a spherically polarized Alfvén wave, where locally the total magnetic field intensity is basically constant, and the tip of the vector goes on a sphere. So what happens with the solar wind? I'm just giving you here a rundown of the fact that you need to heat this corona, and you need to provide a pointing flux to do that. And part of that pointing flux in the closed field regions ends up in producing the bright radiative loss that you see from the solar corona itself in the polar coronal holes. It really ends up mostly going into the solar wind. There's a little bit of thermal conduction back. And then this gets into kinetic regimes that I cannot really talk about today, but we know that the distribution functions, especially in the fast winds, are animals that are pretty anisotropic and clearly not thermodynamic in nature. A final thing is that the asymptotic wind speed of the sun can be quickly calculated as being essentially the difference between the pointing flux or the mechanical energy flux that you put in, the total energy that's lost, the total flux of energy lost via radiation that counts in the sort of the closed regions and doesn't count a coronal hole, divided by the mass flux. And then you have to subtract the escape speed from the sun squared. So what happens is that your asymptotic wind speed depends on this ratio, Fm over m dot. If you have a region of the sun with a larger mass flux, but a similar energy flux, then of course you get a lower asymptotic wind speed. That asymptotic wind speed and the mass flux are related because essentially the amount of mass that expands from a certain region of the sun, it depends on the density profile. And that density profile depends on essentially the base velocity of the solar wind, which depends on the expansion factor of a single flux tube that you're doing. And what this shows is essentially the base speed of the solar wind, apart from the exponential, which in this particular context doesn't matter too much. It's basically the coronal thermal speed or the effective thermal speed times the expansion between the expansion factor of a flux tube between the critical point where the wind becomes supersonic and the coronal base. And what this means is that if you have a huge expansion factor, you increase the base speed. Because the density profile is essentially static until the sonic point, that increase in base speed increases the mass flux and therefore reduces the asymptotic wind speed. So you have an anticorrelation of solar wind speed with expansion factor of the magnetic field. And I'll come to this in a few minutes for what we're considering. Pointing flux comes from a mess, which has to do with the chromosphere. There are entire space missions devoted to the chromosphere, so I'm not going to really discuss the details, but clearly important dynamical phenomena are occurring. There are wave modes coming from the chromosphere at 2-3 minutes, and there's magnetic reconnection due to the continuous buffeting of magnetic fields coming from the sides here. And solar orbiter, which is the first spacecraft to bring telescopes down to essentially the orbit of Mercury, has shown details of how this activity, you have these kind of really tiny flares and microflares that are continuously providing heating in closed regions of the sun. When these reconnection occurs between open and closed field lines, it leads to opening up, what's called interchange reconnection, and that can lead to heating on open field lines. Parker, on the other hand, was trying to, the goal of Parker is really to come to terms with how the different mechanisms that have been hypothesized, wave heating, particle heating, and so on, determine the acceleration of the solar wind and the details of where the different types of solar wind come from. So here we are. This is where Parker is today. As you can see, this is a graph of the distance of Parker in solar radii, and this is days of the mission. We are approaching the final year of the nominal mission. We are now at perihelia that are essentially at 10 solar radii. 11 solar radii, and we are going to have a new Venus flyby, which is going to take us to 9.87 solar radii from sun center. We are about to go into I don't remember the 17th or 18th perihelion. Oh, no, it's actually further. It's 20th perihelion right now, the 20th perihelion. And I can tell you that the spacecraft is autonomous when we get close to the sun. And so we had a beacon, and now the spacecraft is going to be silent, and we expect a post-perihelion beacon on July 2nd. So we're actually coming into our 20th perihelion right now. So let's get into the observations. This is the observations of the magnetic field from the first solar probe perihelion. And what does this show us? It shows us that the magnetic field, as the spacecraft moves closer to the sun, the intensity of the magnetic field goes up, as you can see. At perihelion, we are now at the highest magnetic field measured. This was at 35 solar radii, 90 nanotesla. And then we come back up. But there's this strange phenomenon occurring, as you can see, is that the radial magnetic field is going up and down continuously. Up and down, up and down, up and down, up and down. If you look carefully, you can see it going up. These are New York seconds. So this is really the brute data that came down. And then you can see that there's a baseline magnetic field that's oscillating underneath. And you might ask, what is there? Are you crossing the heliospheric current sheet all these times? I mean, solar probe is in the ecliptic. Well, it turns out that it's not. It turns out that if you look at the pitch angle of energetic particles, the angle doesn't change. So these are actually folds in the magnetic field. And so remember that anecdotal early observation by Ulysses of a few inversions of the radial magnetic field. That's 35 solar radii. The field is a mess. It's full of these turns. And if you look carefully at these turns of the magnetic field, they come in groups or patches. So that was the first kind of really interesting observation from Parker Solar Probe, that the inner heliospheric magnetic field is incredibly complex and tied up in these reversals. One looks at this more carefully. This is again the same first perihelion. You can see the radial magnetic field is in blue. The transverse components in the ecliptic and out of the ecliptic are shown in red and orange here. And the magnitude of the magnetic field is shown in black. And what's obvious from this picture is that the oscillations in the magnitude of the field are at least an order of magnitude, if not more, smaller than the oscillations in the components. This is an inset of 2 hours. And if you look at the magnitude of the field, it's sitting at around 90 nanotesla. It's basically constant. While the magnetic field is inverting, the radial magnetic field is inverting, going from minus 90 all the way up, some cases all the way up to plus 70, as you can see here. That is exactly a spherically polarized Alfvén wave, what you would expect. Magnitude of the magnetic field is constant, except that I haven't mentioned anything about the velocity field. For this to be Alfvén waves, the velocity field has to have a signature as well. Well, this is the plot of the velocity field. And what do you see? You see, we saw an average wind speed that was quite slow, 250 kilometers per second. But you will notice that the oscillations in the velocity field are not symmetric around the mean. There's basically a base line, and then you have upward jets. And if you carefully look, these upward jets are correlated with the radial magnetic field inversions. We were in a negative polarity coronal hole here, and so the jets that you see are positively correlated with the magnetic field. And this means that we are dealing with really large amplitude, spherically polarized Alfvén waves. Miracle difference between what was observed before, we are seeing this in very, very, very slow solar wind. I will be briefly explaining why we see jets going one way in a second. Now let's jump to other encounters to see if this phenomenon was ubiquitous or not. Well, this is the radial magnetic field. I'm sorry, this is the bottom panel now. And you can see that in encounter 9, we get much closer to the sun. This is the measurement of the field in nanotesla. We're now coming down to 400 nanotesla. You can still see these groups of oscillations. They have a harder time inverting the magnetic field. The field is stronger, but you see these large oscillations. And this is the velocity of the plasma measured by span. As a very quick aside, I have to tell you that, that as you can see the measurement, there's something wrong here. Well, the point is that the way the span measurements, the way Solar Probe measures the velocity of the solar wind is essentially using ram effect. The instruments are hiding behind the spacecraft shield. And so when you're moving in on the way into an encounter, getting close to the sun, you're going in the right direction, the wind's coming at you. So the sum of the orbit motion, which is a significant fraction of perihelion, we're going above 150 kilometers per second, so it's a significant fraction of the solar wind speed, adds up with the solar wind speed, and so you can measure these things from the side. When you're coming out on the way back, you have a much harder time because you're running away from the solar wind. And so the aberration is much smaller. We do have a Faraday cup in the front, but sometimes it doesn't work quite correctly. And so that's the reason the velocity measurement here isn't so good. But where you do have good velocity measurements, you see that there is still a correlation between these spikes and so on. This is encounter 12 now. You see these, this is the radial magnetic field. This time it's on the top. You see these beautiful patches of switchbacks. This is the heliospheric current sheet crossing. You kind of see them a little bit on the other side, but you see that the wind is, the magnetic field at least, is different on one side and the other. And again, if you look at the velocity field, you see this correlation. Now the magnetic field is positive, and so the switchbacks are negative, but you still have positive jets. And again, this has to do with the nature of Alfvén waves that I'll be describing previously. So as I told you, switchbacks are Alfvénic. V and B are essentially perfectly correlated. You can see this in red and blue, notwithstanding differences in the cadence of the instruments and so on. You can see that there's this really beautiful correlation between V and B, which identifies these oscillations as Alfvénic. Why do you always have outward jets? So let me explain something about a large amplitude Alfvén wave. Suppose you're in an outward magnetic field. BR is positive, and you create a switchback. You create a delta BR, which turns the field around. Now, if you have an outward Alfvén wave in a positively directed magnetic field, delta U is minus delta B. Delta B is clearly negative, and so you have a delta UR, if BR turns negative, that is positive. Now imagine that you have an average magnetic field that is negative, like so. Now your switchback creates a positive delta BR. But now for an outward Alfvén wave, the correlation between delta U and delta B is the opposite sign, because it depends on the sign of the field in which you're propagating. And so now delta BR is positive, but delta UR has to be equal to delta B, and so it's again positive. So the fact that you have outward jets means that these Alfvénic fluctuations, these large amplitude spherically polarized Alfvén waves, are coming from the sun. So we have this new observation, which basically shows that you have Alfvén waves in all solar wind types. And they are such large amplitude that they invert the magnetic field, not rarely as seen in Ulysses, but all over the place. We hardly ever see this at 1 AU. So we have to ask ourselves, where do these switchbacks come from? How are they formed? So these are possibilities. You can imagine that differences in the velocity will distort a magnetic field and perhaps lead to inversions. Now, a generic velocity structure on a generic magnetic field won't produce an Alfvén wave. However, it will distort the field in the right way. Another possibility is the interchange reconnection I was mentioning before. If you have an open field line that reconnects with a closed field line, there'll be a kink in the field line that will propagate outward as an Alfvén wave. And perhaps that kink remains out to solar probe. That's an impulsive mechanism. There's a third possibility, which is that at the coronal base, you have small amplitude waves, but because of the density decrease with stratification, the amplitude of the waves increases. And so if it increases sufficiently, you will form a switchback. Maybe all of these three mechanisms are working together. So which one looks the best? Generic velocity structures don't look good. They don't produce Alfvén waves. Reconnection doesn't look that good either on its own because the reconnected field straightens out in one nonlinear time. So how about the expansion? The expansion of the solar wind works quite well. This is a numerical simulation that shows it. But perhaps other mechanisms work together as well. This is now showing you what happens if you have, say, a jet, a flow jet or a wake, and you have a magnetic field crossing it. You see you can produce inversions, but they don't have Alfvénic correlations. One way to overcome that is to put Alfvén waves on top of that rather than have a static field, put an Alfvén wave, and that'll produce localized small kinks, but not really the big ones. The third and best possibility is to combine the small amplitude of the waves in the solar corona with a large-scale shear in density or structure on the sun in the lower corona that will produce a distinction in the Alfvén speed along neighboring field lines, and that will allow these fluctuations to evolve into switchbacks. And when you do that properly, therefore allow very small amplitude oscillations, but with a large-scale gradient across, say, the supergranulation structure of the sun, lo and behold, you produce magnetic field switchbacks with velocity field correlations, this picture on the left, which looks very strikingly similar to switchback patches as seen by Parker Solar Probe. This doesn't mean that reconnection doesn't work. Unfortunately, these movies are still, but you would have seen small-scale eruptions. Maybe we can see one here. I'm approaching the 3-minute mark now, so let me go very quickly. So these could be the initiation of an initial Alfvén wave that then becomes a switchback. So this is how interchange reconnection would work. It would generate an Alfvén wave. This kink would straighten out, but it would leave a perturbation that with expansion up to 10 solar radii would lead to inversions seen at the sun. The switchback come in patches. They are correlated with structure on the sun, which is the size of supergranulation. Okay, I'm finishing up here, and I'm essentially going to just very briefly discuss solar wind origins. This is supergranulation to show you that shear will produce switchbacks. We have indication that these switchback patches are associated indirectly with energetic particles. This is a paper that was published in Nature about a year ago. And the general behavior of the system shows that we have a profile for the solar wind speed. This is a histogram of all solar wind speeds, where you can see that the switchback population and the jets produce the speed. I haven't said anything about the origin of solar wind. I don't really have time. Let me just jump to the conclusions here for very quickly, and say one thing. Just let me finish here. Sorry. Okay, close your eyes. There are a number of slides that I haven't had time to get into. I just want to mention the fact that Solar Probe has shown us that Alfvén waves are everywhere in the solar wind that's born. They disappear. The reason they disappear most probably has to do with interaction with the structure of the solar wind, leading to greater heating of regions where the magnetic field is complex and leading to a source for the slower wind. While in regions where the dynamics is not too complicated of the field, they lead to a post-acceleration of the wind to the higher wind speeds. This is a new result from Parker Solar Probe. Conjunctions between orbiter and probe have been used to understand this evolution of these patches and its present work. I've completely skipped the instability of the heliospheric current sheet. I don't have time to discuss it, but we now know that the opening of the closed magnetic field in the equatorial regions occurs necessarily in intermittent fashion. It's associated with what's called fast magnetic reconnection and ideal tearing. And we can now have measurements that essentially verify the hypotheses underlying that loss of confinement, which is related to ballooning type modes at the vertex, on top of the closed helmet streamers, and then very fast tearing along the forming geospheric current sheet. And I'll stop there. Thank you.
Much. I'm the chair. I'm taking the phone for the moment. We have time for at least one question over here. And I guess I have to repeat the question. But...
Very nice review, Mark. Can you state how the Parker Solar probes would be more beneficial to expand it to how stellar fields and stellar winds?
Okay, the question, did you hear it?
No, it was kind of lossy. So if you could repeat it very quickly.
Question was from Offer Cohen. The question was, would Parker probe be more beneficial for stellar observations, if I got it correctly? Stellar winds and stellar magnetic winds.
Well, I think essentially it's teaching us something about the nature of the way the magnetic field disconnects from the star. And so, again, the sun is our Rosetta Stone. So my impression is that a lot of the studies that I've just described very, very briefly, unfortunately, apply even more so to the heating and acceleration of stellar winds. So really, it's a map. What we found is that intermediate region, which is very difficult to observe between the visible corona with its structure and the in situ, is actually host to a turbulence regime that essentially nobody expected. And so the implications of this for other stars need to be discussed and understood.
Okay, we're going to have a quick question by Andrea Dupree. Maybe you can try to take the phone.
Can you tell us whether Parker has suffered a CME and what was observed? A coronal.
Oh, okay. Yeah, sorry. Yeah, I completely overlooked that. That would be a whole, we could have gone on for hours. We crossed more than one CME, and we survived. So far, so good. We're now at solar maximum, so we hope, cross our fingers, that all keeps going well. But we now have very, very detailed observations of the structure of a CME, of the flux rope nature. We've seen even some cold material associated with the original filament. And so, again, the energetic particles accelerated by the shock. We see instabilities in the envelope of the CME, Kelvin-Helmholtz type instabilities on the flanks. And so we're really doing now the detailed physics of an expanding CME in a way that hadn't been done before. Again, I would like to remark on the fact that we have one remote sensing instrument, WHISPER, which I didn't have time. Let me cheat and just show you one movie of the blobby nature of the origin of the sort of streamer wind, as we just briefly discussed it. So we also have seen a CME, and thanks to the WHISPER spacecraft, we're actually seeing remote sensing measurements that can be combined with in situ to really reconstruct the structure of the CME itself.
Okay, let's thank Marco once more. We're setting up the next talk by Doug Evansberger from Leiden Observatory.
Okay. Good morning, everyone.